detector. It's using data mining approach to earthquake detection, so it's looking at it in a little bit different way. It can reduce the false detections using a multi-station extension. It's, as I mentioned before, it's sort of complementary to other techniques, and there's certain trade-offs. And I'll just skip to the end, and I'll take questions.
Thank you, Karianne. Very nice and informative talk. So it's the most detailed talk about the FAST I've ever heard. So thank you. You have many collaborators here, and we also need your help to run the code for our micro and picoseismicities, because we have many beautiful data sets, continuous data set from micro to picoseismicities. So thank you. So I think we have time for one more quick question. So anyone have a question?
Yeah, and I can also, I'll stay here and eat my food, so I can ask more questions after.
Okay, great. I think the audience asked many questions during your talk, so thank you.
Yeah, so I'll just put this up here too quickly, which is I'm just starting a postdoc. I'm looking for new collaborators, so if any of these kind of data science topics might be relevant to your data sets, like I would be interested in. I'm interested in like how do we incorporate physics and domain knowledge into machine learning? How do we learn when we don't have huge labeled data sets, like if we have messy data sets, smaller numbers of labels, this kind of thing. And also what we can do with some of these non-traditional data sources, which are where you have a lot of data, but it's kind of messier, and how do we extract interesting signals from that? So just put that out there if anyone wants to chat more about these things.
So one quick question. What was the largest data set you actually processed in terabytes?
Well, so
in bytes of some regards.
yeah. Well, okay. So it can go back to here. So this is like 10 years of data, and this one was, I want to say 11 stations. We had like 30 channels, something like that. So I don't know how big that was in terms of like how all the files, because actually when you compute the fingerprints and stuff like that, file size, because it actually is bigger because you have like sort of the way that it gets, I don't know, it ends up being larger in many cases. And then you also have your sort of output files, which can be really large before you eliminate. Like when you just get for the sparse similarity matrix for a single station, if that station is really noisy, that can be like it's not always that sparse. And so it sort of depends on, like all of those files are big, but this would be, in this case, we would have 10 years of data that's sampled at 100 hertz in each station. So we had 11 stations, and for most of them we had 3 channels. And so I don't remember how much space that data set is. But we had to run this on a machine that had a terabyte of memory. And so that was the data. Our computer science collaborators have their own cluster that they were able to run it on. So these were on terabyte machines. And so if you do run the code, if you want to run it on a really huge data set, like don't run it on your laptop, because it requires a lot of memory. So for like the Iquique data set, where I'm running 2 weeks of data and 5 channels, I could do that on my laptop. But if you want to run 10 years of data, and this code also has to be run on a Linux cluster. We haven't tested it for like use on a laptop, although I don't know, I have a version that I run on my laptop, but this version with all the parallelization and optimizations is designed and has been tested for a Linux cluster. So those are the caveats.
Yeah, let's thank our speaker again.